Okay, so welcome to the 3:30 slot. This is Nicholas Barrett, mentored by Dr. Daniel Gold, and his talk is titled Developing a Transcriptomic Atlas with a Greater Parasite Labaricola migrator.
As Dr. Boyer mentioned, my name is Nicholas Barrett, and today I will be talking to you all about my efforts to develop a transcriptomic atlas for the greater parasite Barrett migrator, which infects the Madagascar pheasant cockroach, Bronchodiarrhea portentosa. So as you can see from this graph, infectious and parasitic diseases are a massive burden on global health. They make up about a quarter of deaths worldwide and are only second behind cardiovascular diseases. Of these infectious and parasitic diseases, diarrheal diseases are a major killer. They make up about 1/3 of the total deaths due to infectious and parasitic diseases. And this is especially a problem in the developing world, as I will discuss more later. But they can also be a major problem in developed countries such as America. Cryptosporidium, the causal agent of cryptosporidosis, is actually one of the major causes of infant diarrheal diseases. It is second behind rotavirus, and it causes moderate to severe diarrheal disease in infants. Cryptosporidium are what is called an oral fecal pathogen, meaning that they are excreted from their host. And this thick-walled oocyst that is environmentally stable and leach resistant, this resides in the environment and can persist for long periods of time until it is ingested by its next host, wherein it infects the epithelial lining and continues the cycle, producing more oocysts and releasing them into the environment. As you can imagine, this is a problem in nations that do not have adequate waste treatment facilities, or when there's a contamination of a waste treatment facility into a public water supply. Now, once they enter the host in the form of this oocyst, the oocyst releases sporozoites. These sporozoites are the invasive stage of the parasite. They infect the epithelial lining of their host. They then turn into a trophozoite stage that resides in the epithelial lining. This trophozoite stage can undergo both asexual and sexual reproduction. And this results in the production of more oocysts that are released into the environment to infect subsequent hosts. So other parasites, such as toxoplasma right here, are intracellular, or such as Giardia right here, extracellular. Unlike either of these, Cryptosporidium are epicellular, meaning that they bind just on the edge of their host epithelial cells. And so because they are somewhat unique in this manner, there is not very much known about what occurs in this interaction. All that is known is from these ultrastructure studies taken here of a Cryptosporidium carbon parasite that is infecting a mouse jejunal epithelium. And one of the main things that is known is that there's this feeder organelle at the interface between the two organisms. It's hypothesized to be involved in nutrient transduction between the host into the pathogen. However, the molecular mechanisms of this transduction are not known. Now, working with Cryptosporidium is not easy. The work needed to elucidate the molecular mechanisms of its infection with its host requires the creation of transgenic parasites. This requires the use of knockout mice and cattle to produce the oocyst. However, neither of these are cheap, and this is quite a barrier for research with Cryptosporidium. Additionally, because Cryptosporidium infects humans, any work that is done with these parasites must be done at high levels of biosafety so as to limit the potential for parasites to infect researchers. Now, recent phylogenetic studies conducted on single-cell parasites or single-cell organisms have found that parasites, Gregorins, seen here, are actually highly related to Cryptosporidium. They're in fact each other's closest ancestor. They're more related to each other than either of them are to other apoplectin parasites such as Plasmodium, the causal agent of malaria, or Toxoplasma, the causal agent of toxoplasmosis. Like Cryptosporidium, Gregorins also infect the host epithelial lining. So as you can see here, the Gregorin and the Gregorin life cycle, they release oocysts that then themselves release sporozoites that infect the epithelial lining, which is denoted here by this line. The sporozoites are the invasive stage, they infect the epithelial lining, and then they mature into trophozoites, as occurs in Cryptosporidium. These trophozoites then proceed as they do in Cryptosporidium. One of the major differences between the two is that Gregorins are released from their host in the form of this gametocyst, whereas Cryptosporidiums are released just in the oocyst itself. This means that within this gametocyst are the oocyst, and within the oocyst are the sporozoites, so it makes it harder to access the actual organisms inside, and that potentially relates to their environmental stability. Another difference between the two is that Gregorins infect invertebrates, such as the Madagascar hissing cockroach, Chronophotoroina portentosa, that we will be using and have been using in our research. Now, in addition to these similarities in their life cycle, Gregorins, like Cryptosporidium, are also epicellular. And so you can see here the mature trophozoites are bound to that epithelial lining, where they will grow, feed, and eventually reproduce, producing more gametocysts. You can see there are slight differences between the two, but essentially they are the same. And so the purpose of our study is to determine the stage-specific gene regulatory elements that are involved in this interface right here, and the virulent factors that are involved in Gregorin parasitism. In order to do this, we will be using RNA-seq and creating gene expression maps, as I mentioned in my title, the transcriptomic habits. And this is not new or novel. It has been done in other parasites, but not in Gregorins. And so you can see here an example of Plasmodium in its red blood cell infecting stage. Here it is. Its different life cycle stages as it matures in the red blood cells. And you can see here the research done on this using RNA-seq and transcriptomic analyses produces a heat map that shows you the level of expression of different genes at different points in the life cycle. So the darker it is, the higher expressed the gene is. So you can see genes like this are higher expressed in the ring stage right here, but then as the parasite matures, they become lower expressed. Now, because we have not yet received backup data from the RNA sequencing analysis, I created a hypothetical gene expression map. So you can see here just a reminder of the Gregorin life cycle within its host. And here's the quantitative gene expression map that I created. So this is basically what we expect, where you have low expression of genes that are involved in epithelial binding in the life cycle stages that aren't inside the host. But then the life cycle stage that is bound inside the host, mainly the mature trophozoite, has high expression denoted by the ibis color. And then when it goes to the mature trophozoite stage, right here, it releases from the epithelium and no longer expresses the epithelial binding proteins, and so that's a low expression. And that's just an example of what we expect to find from our RNA sequencing analysis. Now, in order to conduct this research and extract the RNA, we first plated our Madagascar hissing cockroaches in these Carolina dishes. This is the protocol that Matt was discussing. We then let them sit overnight for 24 to 48 hours, and then we sorted their frass and collected the gametocysts seen here. We then allowed the gametocysts to dehiss, which is where they release their oocysts. and that normally takes about 48 hours. And then from the glue assist, we performed an RNA extraction to extract the genetic material, specifically the RNA, and isolate it. Now, in doing this, we had many challenges. For one, we started with the gamete assist, but as I mentioned earlier, the gamete assist is essentially extra protective of the sporozoites, and it is extra environmentally stable, and so it is harder to access the genetic information that lies inside without damaging the RNA. And so in our first attempt, we made 50 of these plates, and we only got one gamete assist. And so from here, basically our challenge was that we had an unreliable source of gamete. That's not sustainable to make 50 of these plates and only get one gamete assist, just one single gamete assist. And this solution was discussed in the project and is still ongoing. In our second attempt, we made 24 of these plates, and we were able to get 26 gamete assists. You can see that our numbers greatly increased due to changes to our protocol, but we were still unable to isolate RNA. And so this is where we made a change from isolating the RNA from the gamete assist to the glue assist, because we hypothesized that the procedure that we were using to isolate the RNA from the gamete assist was too harsh and was degrading the RNA. And so by extracting it from the glue assist, we basically reduced the amount of destruction of the RNA and improved our RNA integrity. In our third attempt, we made 23 of these plates, and we received 7, so you can see gamete assist. So you can see that we were still having problems maintaining or acquiring a reliable source of gamete assist, and we were still unable to isolate the RNA. So we improved our cleanliness. We washed these gamete assists multiple times prior to extraction, and that seemed to change. So in our fourth attempt, we made 25 plates. We're still having problems with gamete assist, reliable gamete assist collection, and we did receive RNA, but it was in low yield. So here, our remedy was to reduce the number of freeze-thaw cycles needed to crack the glue assist and access the genetic information from 5 to 2, and this we believe improved the integrity of our RNA and made it more able for us to extract from the next one. And so in our fifth attempt and final attempt as of yet, we made 25 plates, seen here. We extracted 11 gamete assists, and we have yet to hear back from any problems, but we believe that this RNA is stable and we're ready to go back. And so for my acknowledgements, I'd like to thank Dr. Gold and my fellow Gold Lab members, the Hope Fellowship that Matthew Fensel and I received, and Dr. Richard Houghton for Bruce Fellowship.
We have time for some questions. Well, I have a question since I was present that we're working out the first stages of what we're going to develop. What have you learned about the ability to adjust and learn from frustrations?
Yeah, so as you saw on the previous slide, we had to make quite a few changes. I think that the key is being able to identify what went wrong or potential things that went wrong, and then kind of be creative and developing solutions for that. And then also maintaining motivation, because each one of these extractions takes like 4 hours tops. And so getting more yield on that, it makes you want to do it less the next week and then it less, especially when you're not getting any RNA consecutive, like multiple times in a row. So pretty much just sticking with it and being creative and coming up with ideas.
This is the first time that I hear this talk, so this is perhaps I'm not the last one, that you can reorient. So when thought that it's better to isolate the oases.
Yeah.
So from there on, we continue isolating from the oasis.
Correct.
Okay.
Right.
So now, if we go back to your home data for the RNA-seq. So there, your predictions would be that the epithelial lining proteins are not going to be expressed.
Correct.
So what are you learning from that particular stage?
Right, okay. So this would allow us to identify or to confirm specific genes that are involved in the binding that could be used as drug targets for targeting gregarin and fructose infections. Is that what you were
So the oasis is the one that is binding?
No, no. So the oocyst is right here, and then the sporozoi is the one that first makes contact with the host cells. And
So
then
that is going to be, so that is not going to show you the binding, yes?
correct. So the oocyst right here would have low expression of epithelial binding proteins.
So what you're telling me that is going to tell you the evidence for binding?
That would be in the trophozoite that is bound to the host.
But you don't have RNA.
Correct.
Have RNA and different.
Correct. So we're currently working on isolating the intestinal stages from the module. We thought we would first establish, basically confirm that we could isolate RNA from these parasites before we started sacrificing our cockroaches by and removing the stages that are actually inside the host. So it's ideally we would have RNA data
Do
from
you have the
all.
RNA-seq data from the baby stages and else this will be on a database?
Right. And so just using the oocyst, that was the easiest one to get us started in doing the, ideally we would have it from all many of the ones that are involved in manufacturing. So using the oocyst is the easiest, yeah.
Okay, so now Dr. Gold will say a few words and place the honor soul on the.
So, since these talks don't rely on the unbelievable amount of work that has gone into this, because Nick and Matt, they were in my parasitology class my first semester here, and it was 2 years ago, their junior year, fall junior year, and they both joined the lab at the same time. When I say they joined the lab, what they meant, but the lab was a figment of my imagination, it did not exist. My pitch to them was that I'm interested in these weird parasites that no one cares about, that infect invertebrates, and I've never worked on an invertebrate, and I don't actually know how to get these parasites. I can resource them. We just have to hope and pray that somehow, some way, we can find insects that will actually come already infected because no one has a source for them. You can just write and say, oh, give me some gregarins. It doesn't exist. And so, their desire to be part of something that was truly new, from the ground up, not something that, a model system that has been well established where you can get genetic strains, something that you literally had to work out every single step yourself because there was no roadmap for it. And that was the pitch, and we have parasites. We have a way of isolating parasites. Do we have all ways of isolating parasites? We do not. But everything, I can honestly say that we would not be here without Nick and Matt and what they did. End of story. And while this project was one of many projects that they actually were working on, the first project was we thought we could do it for beetles, and they managed that early on. We couldn't find a gregarin in any of I had 2 huge tanks of beetles. How many beetles do you think we had?
Hundreds easy.
Ridiculous. Thousands, I would say, right? Not a single parasite to be found, right? We spent a lot of time trying to find them, right? And so the cockroaches, how, you saw the picture that Matt showed the frass, how do you get them from there? That was them, not me. They were the ones who figured it out. Every single step, it was them. They took ownership of it. They made it their own. They came in. I didn't have to harass them to do things. They did it on their own. And while they're toxic, I think I hope it conveys that they have a mastery understanding of the system and what they're doing. This is in no way indicative of the amount of effort and work and just sweat and blood and tears that they put into this, and I am forever grateful for it. And they definitely earned this honor stone. I mean, not a doubt in my mind. And so I just want to make that really clear and put that into context, not just for the people who serve, but for them. So. I admire your adventurous spirit. Because that's what this was. This was an adventure. This was an adventurous spirit. And I didn't have the answers, and so I think that's an important point.